This is chapter 11 for Bio 103, and we're going to talk about mineral resources, the Earth's rocks and rock cycle, geologic hazards, mineral resources, mining impacts, and we'll talk about some sustainable uses of minerals. So our central case study for chapter 11 is the mining of coltan, which is an ore that contains a metal known as tantalum. And this is mined in a location in the Democratic Republic of the Congo. And since 1998, this nation has been in almost a constant state of war. Soldiers who have taken control of the mining operations have been forcing farmers and others to work in essentially slave labor to mine for coltan. So in addition to the environmental impact of the coltan mining, this has caused lots of human rights abuses as well. And because of this, many electronic manufacturers are under tremendous pressure by activist groups and human rights organizations to not buy their coltan from the Democratic Republic of the Congo. Geology is the study of the Earth's physical features, processes, and history. So we're going to talk about some of the raw materials that we extract from the Earth for our benefit. The Earth has a number of layers. The inner part is the core, and the core has an inner and an outer part to it. The inner core is solid iron. The outer core is molten iron. Around the core, there is the mantle. The mantle is a less dense and more elastic kind of rock material. It has a number of layers, including the asthenosphere, which is a very soft or milted layer of rock. And around the mantle is the crust, which is a very thin, brittle, low-density layer of rock. And here we have a cross-section from your text of the Earth. You can see the inner and the outer core here. And up here we have the mantle. You can see a number of parts to the mantle. There's the asthenosphere. Here's the uppermost layer of the mantle. And on top of that is the crust. Now, the crust is not one solid shell. It's actually cracked and broken up into several plates. And these plates are sitting on top of the mantle. And because the mantle is very elastic and milted in places, these plates are being pushed around. As magma rises up from the mantle, it pushes these plates around, causing some plates to move towards each other, others to move away from each other. This has resulted in the continents having combined and separated and recombined themselves over a period of millions of years. The last time all of the continents were joined together, this landmass was called Pangaea. It was about 225 million years ago. So here we see Pangaea right here in the bottom of this drawing. This is where the continents look like when they were all touching together. You can see how South America and Africa were touching there. And you can see if you look at today how South America would fit kind of snuggled right up against Africa. The plates that these two continents were on have been moving away from each other for the last several hundred million years. And you may also see here we have Eurasia, and this is North America, Antarctica, Australia. This little bit here is actually India. India was not part of Eurasia during Pangaea's phase. Instead, it's been migrating towards Eurasia for hundreds of millions of years. Eventually, it collided with Eurasia, and this caused the formation of the Himalayan mountains. And you can see from this map of the world today, we have a variety of plates, and they're different, and they're all moving in different directions. Some are diverging from one another, they're moving away, such as South America and Africa. These two plates are moving away from each other. Others are heading towards each other. They have what's known as a convergent boundary. So here's the Indian-Australian plate. It's called that because it has both India and Australia as part of it. And this plate has been converging, has been colliding with the Eurasian plate the last 100 millions of years. Other plates are moving next to each other. They have what's known as a transform plate boundary. This is the Pacific plate. It's mostly under the ocean, and it has been sliding next to the North American plate. And the boundary between the two is known as the San Andreas Fault, and it's a very famous line here, and it's running through California, and it's one of the reasons why California has quite a bit of earthquakes. Now here we have a drawing of a divergent boundary. Rising magma, which is molten rock, is moving up to the surface. As it does that, it pushes the two plates apart, and as the magma reaches the surface, it cools and forms a long ridge of mountains. So for example, where the South America and the African plates are diverging from one another, the magma is moving up and it's forming the Mid-Atlantic Ridge, which is the world's longest mountain range. It's completely underwater though. Transform plate boundaries are plates that are like the North American and the Pacific plate that are sliding next to each other. And as they do this, they can build up friction and pressure. And when some of that pressure gets released, you end up with an earthquake. Transform boundaries are sometimes referred to as fault lines or faults, such as the San Andreas Fault. And finally, we have the convergent plate boundaries. These are when plates are moving towards one another. What happens often is what's known as subduction, where one plate is sliding underneath the other. It is sliding down and disappearing back into the mantle. And as it does that, it often pushes magma up to the surface, and this magma erupts, forming chains of volcanic mountains or volcanic islands such as Japan or the Philippines. The other thing that can happen at a convergent boundary is what's known as uplift, where the edges of the two plate boundaries get bent upwards, creating a range of mountains. The Himalayan mountains in Eurasia, the Appalachian Mountains here in North America, and the Andes Mountains in South America were all caused by uplift. So tectonic has a big effect on the shapes of the mountains, which can in turn have a big effect on weather patterns and currents by erecting mountains that can serve as barriers, which may prevent rain from reaching certain areas, or it may cause the weather patterns to move around, or as it moves, a lot of the ocean currents, like the North Atlantic current, gets driven and moved from the Gulf of Mexico up this coast of North America and then shifts towards Europe. That movement is largely dictated by the current shape of the continents. It can also affect evolution and extinction. As the continents move around, they can become isolated from one another, and that can influence what species of animals evolve based on those that they have to compete with while they're on the continent. A rock is any solid aggregation of minerals. A mineral is any element or inorganic compound that has these three things: a crystal structure, a specific chemical composition, and distinct physical properties. And minerals are constantly forming new rocks through what's known as the rock cycle, which is through heating and melting and breaking apart and reassembling rocks and minerals to build new rocks. Rocks have a big impact on the soil characteristics of a given area. They can dictate what type of soil is formed in the area, because as rocks get weathered away, wind and wave breaks off little bits, and those little bits then become the mineral component of the soil in the region. So the type of rocks in an area can have a big influence on the type of soil that forms in that area. Now, there are three main types of rocks. The first type is known as igneous rocks. Igneous rocks form when magma cools. So when magma is brought up to the surface, it's often referred to as lava then. Lava is just simply magma released by a volcano. As that magma cools, it forms igneous rocks. The next type of rocks are sedimentary rocks. Sedimentary rocks, as their name implies, are formed by sediments. The sediments are little bits of mineral rock particles that were formed by erosion or some other process that broke the rock into tiny little particles. Those particles can then pile up and be compacted or cemented back together, and when that happens, they're called sedimentary rocks. This compaction process also creates fossils. If you remember from an earlier chapter, we talked about fossils. They're an imprint of the remains of a living thing left in stone. So usually when something dies near or in water, it can get buried in sediments, and over time those sediments will compact and compress and then transform that remains until there's this imprint left behind that looks like the remains of a creature, but it's actually made of rock. And our third type of rock is metamorphic rocks. These are rocks that used to be some other type of rock, whether it was igneous or sedimentary rock, and then they were subjected to some type of tremendous heat or pressure, which then changes its physical form, giving it new properties. And you can look at the rock cycle diagram in your text. Here it is here. You can show the transformation of minerals into different types of rocks as the cycle moves around. There are a number of geologic and natural hazards that are a result of plate tectonics. If you look back at that map, you can see that there's a lot of fault lines that kind of run around the edge of the Pacific Ocean. They call this the Circum-Pacific Belt, or sometimes the Ring of Fire, which is a nice, great, dramatic term. These are very geologic areas. You have lots of subduction zones and lots of fault systems. As a result, this area around the edge of the Pacific Ocean that runs around the world is known as the Ring of Fire, and it has lots of very active volcanoes. You can see a lot of these here. Here's Mount Krakatoa, Mount Tambora. These both erupted in the 1800s. Japan with Mount Fuji, that's still an active volcano. You have Mount St. Helens here in the Pacific Northwest. That last erupted around 1980. And you see all these active volcanoes represented here. There's a curious thing right here in the middle of the Pacific Ocean, though. We have the Hawaiian Islands, which has a number of active volcanoes, including Mount Kilauea and Mount Mauna Loa. But Hawaii is not sitting on a boundary. It's not sitting on a subduction zone or a fault line. It's right in the middle of the Pacific Plate. That's very curious. Hawaii is sitting on top of what's known as a hot spot. For some reason, the mantle underneath Hawaii is very hot. It's got a lot of extra energy. And as a result of that, it's causing magma to be pushed upward to the surface, and it's literally punching holes right through the continent. And that's how those volcanoes form. As I mentioned, earthquake occurs when there's a sudden release of pressure along plate boundaries, and they can do some tremendous damage to life, especially if the homes are built on top of very loose surfaces, wet soils, or if they're on top of a landfill, or if just building codes are very, very poor. So, for example, Haiti is the poorest country in North America. They have no building codes whatsoever. A lot of the construction there is very ramshackle, very, very poor. So when they've had some earthquakes in recent years, it has been especially devastating, simply because the buildings just all collapse. It's very high risk for people's homes to be destroyed and for people to be killed by these earthquakes. But we can build buildings that are more earthquake resistant and reduce a lot of this damage. A volcano is a place where molten rock, hot gases, or ash erupts through the Earth's surface. And as this molten rock comes up to the surface, it can cool and form a mountain, like Mount Kilauea erupting here in this photograph. Lava can flow very slowly or erupt very suddenly. Mount Kilauea is a volcano that has actually been in a constant state of eruption since the early 80s. It's very slow. It's just constantly belching out some lava, and it is in constant state of eruption. But it's a very slow eruption. The lava is just kind of like oozing out and cooling and forming more rock there. A pyroclastic flow, though, is a fast-moving cloud of gas, ash, or rock. One of the most famous pyroclastic flows was the one when Mount Vesuvius erupted in AD 79 and buried the Roman city of Pompeii, killing all of its residents. So lava can exit from rift valleys, ocean ridges, subduction zones, or even the hot spots, as I said, which is what's going on in Hawaii there. Volcanoes can have an environmental impact. The ash can block sunlight. When Mount Pinatubo erupted in 1991, it actually caused an offset to global warming. It caused a little bit of a cooling effect, which offsetted some of the impact of global warming for a few years. Mount Tambora, which erupted in 1816, caused what became known as the year without a summer. It threw so much ash into the air that they had a very cold summer that year. So the weather patterns were changed for that year. And the eruption also killed 70,000 people. So here are some major eruptions. 640,000 years ago, the Yellowstone caldera in Wyoming erupted. This is referred to as a mega eruption, and sometimes this caldera is referred to as a supervolcano. Its magnitude was an 8, and that's the highest point on the scale. There is nothing higher than an 8. So this was a really devastating eruption. If this thing were to blow today, it would bury the entire United States in ash. We're talking civilization ending type of eruption. 6,870 years ago, Mount Mazama erupted. This created Crater Lake in Oregon. AD 79, Mount Vesuvius in Italy erupted. Again, it buried the city of Pompeii. 1850, Mount Tambora erupted, creating the year without a summer. In 1860, 1883, Krakatoa erupted, killed 36,000 people. It was heard 3,000 miles away and affected the weather patterns for 5 years. Mount St. Helens erupted in 1980. It blew the top of the mountain, killed 57 people. Mount Kilauea in Hawaii there. Again, it has been in a constant state of eruption since 1983. It's just a continuous lava flow. It's only a 1 on the scale here, so it's a pretty low-level eruption, but it's just been a continuous release of lava for over 30 years now. 1991, Mount Pinatubo in the Philippines erupted. Threw sulfate aerosols and ash into the air, lowered the global temperature about 0.5 degrees Celsius. In 2010, I'm not even going to try to pronounce this name. I don't know. You know, Icelandic names always look like somebody just pounded their fist on a keyboard. I just don't know how anyone would pronounce this. But this threw a lot of ash in the air. So much ash that it actually shut down air travel throughout Europe for about 4 or 5 days afterwards. Another type of geologic hazard is known as a mass wasting. This is the downslope movement of soil and rock due to gravity. This occurs naturally but can be caused by humans when the soil is loosened or exposed. A landslide is a sudden and severe mass wasting. Mudslides occur when soil, rock, and water are sliding down the hill, often by heavy rains. A lahar is a type of mudslide that's caused when volcanic eruptions melt snow. In 2014, the town of Oso, Washington, was buried in a massive landslide. So these can be extremely devastating. A tsunami is a huge volume of water that is displaced by an earthquake, a volcano, or a landslide. And these can travel thousands of miles, damaging coral reefs and coastal forests, and can cause huge amounts of destruction and devastation, and can cause lots of life, especially considering people live often very close to the coastline. The only thing we can do about tsunamis, we can't stop them from happening, but we can try to do some advanced warning to give people a chance to evacuate the area. Preserving some natural vegetation, such as mangrove forest along the coastline, can decrease some of the wave energy of tsunamis. Now, in March of 2001, Japan hit what was probably the trifecta of disasters. First, they had an earthquake. The earthquake then triggered a tsunami, and the earthquake and tsunami combined killed about 9,000 people, causing hundreds of millions of dollars in damage. The tsunami, in turn, damaged a nuclear power plant. This caused radioactive material to escape from this nuclear power plant. It's still leaking today. So they had an earthquake, a tsunami, and a nuclear power disaster. Really, the only way this could have been worse for Japan would be as if this had also awakened Godzilla and he attacked Tokyo. It was really devastating. There are ways we can worsen or lessen the impacts of these hazards. Anything that contributes to erosion can increase risk of landslides. Living in susceptible areas can also greatly increase the impact of these things. So living coastlines or mountain regions are very attractive, but they are often vulnerable to some of these events. We can engineer things to increase the frequency or decrease the frequency of these hazards. Suppressing fires, clear cutting, mining, damming rivers can make these more frequent or more severe. And of course, greenhouse gases may change rainfall patterns, which may have an impact on some of the flooding and storms that occur. There are a number of technological things we can do to minimize the impact of these things, including building earthquake-resistant structures, early warning systems, preserving reefs and other structures and other living ecosystems around the shorelines, better forestry and other soil management techniques, building codes, and mitigating climate change. Now, I'm going to talk about natural resources that we get from the Earth's crust. There are hundreds of products that we make all the time from these things. This picture just shows some of the things that we use in our everyday lives that are made from mineral resources, including gypsum for this wallboard, aluminum in the soda can, iron in the pen ink there. You have tantalum, which is that coltan again we mentioned at the beginning of the chapter, used to make the cell phone, and so on. Mining is the removal of any non-renewable resource. So in mineral resources, we're talking about the removal of rock, soil, or other material from the Earth's crust to make consumer products from it. One of the first steps is simply finding where high enough concentrations of these sources can be found so that we can mine them in an economic manner. We use a lot of mined minerals extensively. The average America uses about 37,000 pounds of new minerals and fuels every year. The average child born today is predicted to use 3 million pounds of minerals over her life. One mineral resource that we use a lot of is a metal. And a metal is any element that has a lustrous surface. In other words, it's shiny if you polish it. It is opaque, which means you can't see through it. And it's malleable, which means you can change its shape by hammering it. And it's often a good conductor of heat and electricity. Now, metals are not often found in their pure form. Usually they're found in what are known as ores. And an ore is a grouping of minerals from which we can extract a useful metal. So some economically valuable metals that we use include copper, iron, lead, gold, aluminum, and of course, tantalum. But if you look at all the elements on the periodic table, most of them in fact are metals, and we do have some economic use for almost all of them. Because they're found in ores, the ores have to be processed to remove the metal and make them useful for us. This process is called smelting. This is a combination of using heat and chemicals to extract the metal and then make it into a form that we can make use of it as a viable product. Most metals we use are not a pure elemental form. Usually they're what's called an alloy. An alloy is a solid mixture in which a metal has been fused together with another metal or a non-metallic substance. So, for example, steel is an alloy of iron and carbon. And we don't really make stuff out of pure iron. Iron by itself is actually too brittle to be useful for a lot of things we need for it. So even what we call wrought iron is actually a low-carbon steel. So most of what we call iron is actually a form of steel. Other metal alloys include bronze and brass, which are mixtures of copper with elements and metals like zinc or nickel. And of course, as we process the ores, there's always leftover material. These materials are called tailings. Many of these can contain heavy metals or other hazardous chemicals, including cyanide and sulfuric acid. So these have to be disposed of very carefully. Processing these minerals are very water and very energy-intensive processes. So we have to consume a lot of resources just to convert them into something that is useful for us. Getting rid of the tailings is often a difficult and expensive process. Often they're put in one of the surface impoundments. These are big pools that are lined with plastic. that contain these tailings temporarily. Usually they let the water evaporate, and then they left the material that accumulates left over in the pool to be disposed of in a hazardous landfill. And of course, because they're big pools of water, an accident could release them. For example, it's lined with plastic. Plastic liners sometimes tear, allowing these hazardous chemicals to seep into the groundwater. Or they could overflow. If a heavy rainstorm hits the region from a hurricane or something, it can be devastating to the area as well. There are also a number of non-metallic metals and fuels. Sand and gravel, which are used in construction. Phosphates and potash are used in fertilizer. Limestone, salt. Many gemstones, including diamonds and rubies, are also mined. In addition to the impact of coltan, there's also human rights associated with the diamond mining industry. Diamonds that are mined in Angola are used to prolong and fund wars there. Poor people, just like in the coltan mines, are often exploited into slave labor to mine these. So just like in the electronics industry, the precious gemstone industry is under tremendous pressure not to purchase what are known as blood diamonds, diamonds that are mined using human rights abuses. We also mine substances for fuel. This is a picture of uranium ore, which is used in nuclear power. Coal, petroleum, natural gas, and other fossil fuels are not minerals. Remember, minerals are always an inorganic material. Fossil fuels are organic materials, but they are mined from the ground, and so particularly with coal, they're mined often using many of the same techniques as mineral resources are, so we can treat them as mineral resources, at least for the purposes of this discussion. This is a map of the world showing some of the important mineral resources and where they're mined. This is by far not an extensive list of all the places these materials are mined, but it does give you a picture of the global trade in these things. Mining has a lot of impacts on the environment. First of all, it does provide jobs. It does produce economic opportunities, but it also has a big impact on the environment. And there are a number of different mining methods, and they all have their own impacts on the environment. Strip mining is simply the removal of the sand and rock and soil and anything else that was on top of what you want to get at. This material that is on top, this soil and rock, is called overburden. So you just bring in the power machinery and you remove all the overburden to expose the material you want to mine, and then you refill it when you're done mining that area. Strip mining has a lot of environmental impacts. Pretty much, it's very destructive. I mean, you are destroying any plant life or other communities that were on top of the area you want to strip mine. They're gone. They're destroyed. The machinery is all dug and destroyed that all away. Strip mines also have a problem with acid drainage, particularly when you're mining coal. As water infiltrates these mines, it can pick up sulfur compounds, which convert to sulfur dioxide, which can then leach other toxic materials from the rock or lower the pH of streams, killing the fish there, or polluting our drinking water supply. So acid drainage is natural in many places because these materials are found in the crust. Mining greatly exacerbates and makes this problem even worse. Now, there's some writing in your text about the impact of hydraulic fracking and how mine drainage could may be a solution to some of the problems associated with it. Hydraulic fracking uses a lot of water. This water often picks up toxic materials and other stuff that is very hazardous and has to be handled very carefully once it's recovered. There's been some research done on using acid mine drainage to mitigate some of this problem. And this is particularly significant because we're seeing a lot of hydraulic fracking going on in Pennsylvania today. A good portion of the state is under a structure known as the Marcellus Shale Formation. That's the blue area here. And you can see the triangles are active mine drainage sites. These are where we have acid mine going on. The black dots are active oil and gas wells. So could the mine drainage problem be used to mitigate the fracking water problem? Well, some research has been going on. Dr. Van Gosh and his team have developed a process to treat the fracking wastewater using the water from acid mine drainage to remove the pollutants and purify the water. So maybe this could solve two problems with one stone. There's some promising research behind that, and you can read in more details about that in your text. Subsurface mining. This is the oldest way in which we've mined. This is where you dig tunnels deep underground. We've dug shafts that are up to 2.5 miles deep. This is done for lead, zinc, nickel, tin, gold, diamonds, salts, coal, phosphates. It's still widely done in some parts of the world, including in western Pennsylvania. Subsurface mining is the most dangerous form of mining. You're using explosives to blast the tunnels and free up the material you're trying to mine. So there's a danger of collapsing the tunnels, and when you've got several thousand tons of rock over your head, that can be extremely devastating. There's also toxic fumes, including natural gas pockets that might leak into the shafts and cause workers to suffocate. This is why they used to bring canaries into the coal mine, because the canary would react to the natural gas leak before miners knew it was happening. Natural gas doesn't have a natural odor to it. If you've smelled natural gas in your home, at a stove or anything like that, that's actually an additive they put in the natural gas. Normally, natural gas is mostly methane, which is colorless and odorless, so you can't see it or smell it. So the only way they would know if natural gas was building up in the mine shaft would be if the canary keeled over and died. If that happened, they knew it was time to get out. Now, today they have electronic gas detectors that they use instead of canaries, so they no longer do that. So that's good for the canaries. And of course, there's other problems associated with mining, including coal dust, which can lead to black lung disease, which shorted the lives of many coal miners. And of course, collapsed tunnels can also cause sinkholes, which can be devastating to the surface area. Open pit mining is digging a big hole in the ground to extract evenly distributed materials. And this is often done with copper, iron, gold, diamonds, and coal. Quarries are open pits that are used to mine for often mineral resources that are used in construction, including clay, gravel, sand, stone. Huge amounts of rock are removed to get this. And like strip mining, it pretty much destroys everything that was on top of this area before they dug the pit. These abandoned pits can fill with water, and they can also have problems with acid drainage. The world's largest open pit mine is in Utah. It's 2.5 miles across and 3/4 of a mile deep. Placer mining, also known as panning sometimes, is when they sift through the sediments looking for traces of material. It's often used for gold and gems. If you've ever seen movies about the old gold rush in California, where you see the guys panning for gold, this is placing mining. You're sifting through the sediments looking for usable materials. Placer mining is also how they mine for coltan in the Democratic Republic of the Congo. Placer mining has an impact, including it causes lots of debris to wash into the stream, which can damage wildlife. It also damages the life on the stream banks and causes more erosion problems. Mountaintop removal is pretty much only done in the Appalachian Mountains to mine for coal. And this is where they use explosives to just blow the top off the mountain and then dump the debris into the valleys. Has a lot of impact on the area. It causes water pollution in the streams. Of course, deforestation. It can cause erosion, mudslides, and biodiversity loss. The mine blasting cracks the foundations of the buildings and walls nearby, causes floods and rock slides. Coal dust has been linked to a number of illnesses to people in Appalachia. Critics have also argued that it violates the Clean Water Act by dumping the debris into the local valley. For a long time, they were exempt from clean water regulations. But in 2010, the EPA announced they were introducing rules to limit the damage. Solution mining, or in situ recovery, is where you inject water or some other liquid into holes that are drilled in the ground and then pump up the dissolved material you want to mine. So something that readily dissolves, like salt, this is a common way to mine for these materials. Also lithium, boron, uranium, copper are mined this way. It has less environmental impact than other methods, but the acids and heavy metals and uranium can accidentally leak and get into the groundwater. There's some mining in the ocean where we extract some minerals by dredging the ocean floor or extracting things like magnesium from the seawater. Manganese nodules are small ball-shaped ores that are scattered across the ocean floor. These could be a potential resource, but so far, current techniques cost more than the manganese is worth, so it's still just a theoretical possibility. Once you've mined out an area, you have to reclaim it. You have to put fresh topsoil in place and replant some vegetation. This is called reclamation, and this is required in all developed countries as part of the regulations. So before you get a permit to mine a given area, you have to submit your reclamation plan to the local state agency and demonstrate that you are going to reclaim the area and restore it to at least some semblance of what it looked like before. The U.S. Surface Mining Control and Reclamation Act of 1977 mandates restoration and also requires that companies must post a bond to cover restoration costs. Before that, what companies often do is once they were done mining, they would declare bankruptcy and dissolve the company and then stick the taxpayers with the cost of reclaiming the area. Now they're required to post bonds so that there's money guaranteed to be there to cover restoration costs once the mining is completed. Even with reclamation, it still can not always be exactly what it was. Many of the complex communities are simplified. It's a very difficult and expensive process. And sometimes they don't always duplicate all the essential symbioses. So it can look like a healthy ecosystem, but sometimes they're not always successful with it. Another important law that relates to mining is the General Mining Act of 1872. Yes, 1872. That's how old this law is. This was passed to encourage mining on federal land. If you remember, going back a few chapters, how most of the land in the western part of the country is controlled by the federal government still. Under the General Mining Act, any citizen or company can stake a claim on the mining rights of federal land for $5 an acre. That's $5 an acre. And I'm sure that was considered a hefty sum back in 1872, but that's it. That's what the public gets. The miner then gets all the profits from the mining, and that's it. Supporters of the General Mining Act say it encourages a domestic industry that has a lot of risk to it and lots of investment up front. Critics say that it is giving away valuable land at basically really bargain basement prices. And some people have developed the land for things like building condos that have nothing to do with mining. But any effort to amend the act or even increase that fee have failed in Congress. So another thing we have to be concerned about is the fact that minerals are non-renewable. Once the reserves are gone, they're gone. By some estimates, indium, which is used in LCD screens, might last only about 30 years. Gallium and platinum are also scarce and are of concern that they may run out. Estimating reserves is often difficult, though. New discoveries, new technologies, which may increase or decrease the demand for these. For example, if somebody discovers a new product that requires the use of indium, that 30-year estimate for indium might get much smaller. Or if they discover a way to make these flat screens without using indium, then the estimates for the lifetime of indium may grow longer because the demand will go down. So these changing patterns may have an impact on how long these things will last. As minerals become scarcer, prices will rise. This bar graph from your text shows some of the years remaining of some specific minerals. The reddish ones are the economically recoverable estimates. The orangish ones are the technically recoverable. So what that means is technically recoverable means based on our current available technologies, this is what we can physically recover from the ground. The red bars, though, that's what's profitable. So long before we get to the end of the technically recoverable reserves, we will reach the ends of what's known as the economically recoverable reserves. So at that point, the mines will shut down because they will no longer be profitable, because it will cost the miners more than what they can sell the material for. Now, of course, these estimates may change if there's any changes in the technologies, if there's some improvements in which we can make some of these resources more recoverable, if we can increase the economically recoverable aspect. So, for example, one of the reasons why there's such a big boom to drill for natural gas in the Marcellus Shale is that in recent years there's been improvements in some of these fracking technologies, which has made it profitable now. 30 years ago, drilling in the Marcellus Shale wasn't profitable at all. Today it is, because there's been improvements. So these discoveries of new extraction technologies can change some of these economically recoverable estimates. So, of course, changes in consumption patterns or changes in technology, or if there's more recycling. So recycling minerals can help us address some of the finite supply issues and some of the environmental damage associated with them. So recycling also uses less energy and emits lower greenhouse gases than the mining and other techniques. Electronic waste, or e-waste, is of particular concern because there's lots of minerals and lots of other hazardous materials that go into making these things. So it's not advisable to put these in landfills. E-waste is often very recyclable. There's all kinds of rare materials that go in to make, particularly, for example, a typical cell phone, including gold and copper and palladium and indium and arsenic, petroleum and manganese. So a lot of cell phones today can be resold and refurbished or simply dismantled and their components recycled. And that brings us to the end of chapter 11. So we talked about geologic processes, we talked about mineral resources and mining techniques, we talked about some restoration issues and regulations associated with mining, and we mentioned recycling and sustainable use of mineral resources.